Alright, so in this video, we're going to go over the basics of how to design a flexural member. Now, there are many different cases and scenarios when it comes to flexural members that it's hard to go through and pick out exactly which particular scenario you're going to be using. However, I feel like if you know where to go, then you'll be able to just follow the outline in that section and you'll be able to design the flexural member. So the first thing that you need to know is that flexural members are going to be found in Chapter F. Everything you need to know is going to be in Chapter F. So just on the page next to where it says Chapter F, Design of Members for Flexure, you're going to find this table user note F1.1, and that's separated into different columns. So as we go across, it's section in Chapter F, cross-section, flange slenderness, and web slenderness. So if we can figure out our cross-section and the slenderness of our web and flange, then we can go over to the far left column of that table and it'll tell us which section we need to go to, and that section will give us the limit states we need to check for that section. So the most important thing you're going to need to know is how to determine the slenderness of your flange and your web. And that's all based off of this graph right here. So each member is going to have a lambda value associated with it, and it's going to have a different lambda for the web and a different lambda for the flange. So you can find those in this table right here, and that's just the table that you would go to if you were looking for like the area of your section or the moment of inertia. It's all in that table. The lambda values are tabulated for you there as well. And this also gives you the equations for how they found that lambda value if you're interested in that as well. But you pull your lambda value off of that table and you plot it along this line right here. And that will tell you if your section is compact, non-compact, or slender. So in order for you to graph it, you're going to have to figure out your lambda P and your lambda R. So let's go ahead and clean this up a bit. So your lambda P and your lambda R are going to come from table B4.1b. And it's really, really important that it's B and not A, because table B4.1a is only for members in axial compression, but we're looking for members subject to flexure. So you got to make sure that you're looking at table B. All right, and so that table gives you a bunch of different cases, and then it'll give you your equation for lambda P and lambda R. For example, if we take a look at case 10, it says flanges of rolled eye-shaped sections, channels, and T's. So if you have just your, say this is like a W21 by 62, then you would use case 10 to get your lambda P for your flange and your lambda R for your flange. And then same goes for case 16, except that's going to be your lambda P for your web and your lambda R for your web. But there's some situations where you might not be using an I section, so you just read through the description of the case and then you use that specific equation to find your lambda P and your lambda R. So we can see that if your lambda for your section is less than lambda p, then you're going to have a compact section. Now, if lambda is greater than lambda p but less than lambda r, you're going to have a non-compact section. And if your lambda is greater than lambda r, you're going to have a slender section. And those are all abbreviated in that user note table on page 16.1-45. A compact is abbreviated just as C, non-compact is NC, and slender is S. So if you had a section that had compact flanges and compact web, then you'd go over to the left column and you'd see that you'd go to section F2. And again, it does that for all your different shapes and slenderness scenarios. So again, it's hard to just be able to go through each of those sections and all the different scenarios within those individual sections. But one thing that I do want to point out is this lateral torsional buckling. You're going to see that quite a bit in design. And the most important thing to realize about that is that it's based on this unbraced length. And so you're going to use this graph here to determine if your section is going to behave plastically, inelastically, or elastically. And so your LB is just your unbraced length. And then you can determine your LP and your LR based on equations in the section where lateral torsional buckling applies. They're all given there. But your LP and your LR are going to be based on the CB value. And I just wanted to point out that you're going to determine CB using this equation right here, F1-1, and that's just found on the back side page of where that table user note that we were talking about earlier is found. And you're just going to use that equation to determine CB. But also, CB is tabulated for simply supported beams, and it's table 3-1, so that's quite a bit earlier in your manual, but you can pull a CB value for simply supported beams from that table 3-1. Now again, I apologize that we can't go through every scenario, but if you do come across a problem where you're just not quite understanding where to go or what to do, head over to our homework help page and we'll be able to get all the answers that you need there.